Okay, thank you for the invitation. So I'm going to present a joint work with Olivia Caramello about sheaves on bicategories and enrichment over bicategories. So first of all, bicategories are one of several definitions for two categories. So they are a generalization of, yes, it's too loud, of monoidal categories. So we know how to use monoidal categories for enrichment theory. So here we are going to present how to use bicategories for that. So this is a notion which already exists for some time. There is an article by Street explaining how to enrich in a bicategory, and which explained that the category generalized the theory of enrichment over monoidal categories. On the other hand, there is a theory of enrichment over quantaloids, which has been presented by Professor Izar Stubel last week. And enriching in bicategories is also a generalization of this notion of enrichment because quantaloids are a particular case of bicategories, a case where the two structure is given by partial orders. So we quickly recall some facts from locale theory. So there is several definitions for sheaves over locale, and here is the one which we use to generalize to bicategories. So a sheaf on a locale can be seen as a set together with a local equality. So the set is going to be seen as a set of sections of the sheaf, and the local equality is going to be the greatest open over which the two sections are equal. So this description of sheaves over local can be extended to quantals and quantaloids. So quantals have been presented this morning. They are a non-commutative generalization of locales. So quantal is a complete lattice in which there is an additional operation which can be seen as a non-commutative intersection. And while in a locale we ask that joins distribute over meets, in a quantal we will ask that joins distribute over this additional operation. So in particular, any locale is a commutative quantal in which the operation coincides with the meet. As for locale, we can take the definition of sheaves on locales as set with local equality to define a set with local equality on quantals, and we need more conditions to recover sheaves. And in particular, we have that we recovered the notion of sheaf over a locale in the particular case when the quantal is a locale. So a quantaloid is, again, generalization of quantal, which is a multi-object generalization in which, so it's a category in which the home sets are actually home posets. So it is a category enriched in soup, where soup is the monoidal categories of soup lattices, complete lattices, and joint theory maps between them. We ask, so we wrote there a detailed, concrete definition. So we ask that, so the arrows can be compared if they are in the same home set, and we ask that the order relation respect composition, and the composition respect joins too. So for example, if we have two arrows U and V with U lower than V, then if we can compose with some F and G, we will have FU lower than FV and UG lower than VG. And the same, we ask that the composition respect joins. So it is possible to define sheaves over quantaloid, again, by speaking about sets with local equality. But there, while in a quantal, we have only one object, because a quantal is actually just a one-object quantaloid. To see a quantal like a one-object quantaloid, we just need to see that the additional operation on the quantal can be seen as the composition of arrows. So the elements of the quantal seen as a complete lattice are going to be represented as the arrows of the quantaloid. And we can express sheaves over a quantaloid using a notion of enrichment over that quantaloid, which is the first time we saw it, it's not immediately obvious that this is the same thing as enrichment over monoidal category, but it happens to be if we take the broader look, the broader view from the theory of enrichment over bicategory. So we want to enrich over this quantaloid. This enrichment over the quantaloid is what enables to define sheaves over the quantaloids. So here I wrote a definition, which is we take from the quantaloid Q, you construct another quantaloid pair of Q, and on this other quantaloid, you will take enriched categories, which are skeletal and Cauchy complete. So what does it mean, skeletal, Cauchy? Yes, I will just explain. But yeah, I will explain, because I will present it for bicategories in general, and it will be the same. So I talked quickly about a sheaf of Q before passing to the bicategorical case. So sheaves on quantaloid, they do generalize sheaves on quantal and on locales, because we can just take the local as a quantal and take the sheaves over quantaloid. And they even generalize sheaves on sites, because from any site we can create a quantaloid associated to this site such that the sheaves over this site is the same as the sheaves over the quantaloid we obtain from that. In general, so that means that categories of the form sheaf of Q will be including grothending toposes. In general, sheaf of Q must not necessarily be a grothending topos because, for example, the lattices of subobjects will not always be locales. Yes. So now we go to bicategories, and what we are going to do is re-express the definitions from quantaloid enrichment theory in the case of bicategories. So we will define the skeletal complete bicategories. So a bicategory are a particular kind of two category, or it's a particular definition. It's the one in which so we have the objects, we have the one cells between the object and the two cells between the one cells, and we ask that the commutativity and associativity and unitality of the composition of one cell is respected up to isomorphism. In other definitions, we only ask that either it is a strictly associative, it's a strict two category, or that there is a morphism, this is a lax two category. So bicategory is between that. So more precisely, yes, I give a definition. So yes, what is to be noted is that we have a composition functors, meaning that we have two kinds of composition for two cells. The normal composition between in the home category, and the other composition called the horizontal composition. So more than just two objects, there are several coherent conditions which make it so that everything goes well. So examples of bicategories include monoidal categories. So what is an important fact about bicategories is that they are multi-object generalization of monoidal categories. In that bicategory, one object, a monoidal category can be seen as a one-object bicategory. So again, it was like we did from quantal to quantaloids. The objects of the monoidal categories are going to be seen as the one cells of the B category, and because the B category only has one object, all the one cells are in the same home category, and the arrows of the base monoidal category are going to be two cells of this B category. And what happens is that the coherent condition for the B category with one object and for the monoidal category do coincide. That means that we have it's really the same thing. So quantaloids are also a particular case of B category. So we have all our objects of quantaloids and our arrow between them. And because a poset can be seen as a category, we say that between two arrows, the poset is just a category, posetal category. So this is a particular case of big category. One thing is that the joins in the quantaloid, the join of arrows in the quantaloid, here it will be just colimits in the home category, the corresponding home categories. So in general, we will ask for the B category with which we work to be locally co-complete, meaning that we want the home category to have all colimits we could use. Another important thing that we will ask for the B category with which we will work is that it is closed. So this is the same thing as asking that a monoidal category is closed. In a monoidal category, we ask to have the internal home Here, if we go to the level of arrows, because the big monoidal category is a bicategory with one object, it will be reframed in terms of can extension and can lift. So we will ask that every home category admits can extension and can lift. It will enable us to work with all kinds of colimits, in particular with coends, which will be what enable us to compute composition of matrices. So now we define bicategories. So a bicategory is the data of a pair comprising a matrix and a set. So the set will be a typed set like it was for Quantaloids. So A is the set, N is the matrix. So to any object, little a of A, we associate an object of the bicategory, B. So there is a typing function, which is just a function. And we have a matrix over A, which is to say that for any elements A and B in A, we have an arrow going from the type of B to the type of A. This can be seen in two ways, either as the local equalities that there were for locales, or as a home set in the case where M will be just the usual home functor. So we also ask to have two idempotency or transitivity and reflexivity tool cells. They are what replaces the inequalities that we have in quantals or quantaloid. So, and we have also some conditions, some coherent conditions, which I didn't write there. And what happened is that this theory of enrichment already recovers the theory of enrichment over a monoidal category, meaning that a B category, when B is the bicategory corresponding to a monoidal category, it will give the same object. So monoidal enrich and bicategory enrich will be the same. And this also recovers the notion of enrichment in a quantaloid, which was used to define sheaves. So now we will make it into a category of B categories by defining B functors. So a B functor will be a type-preserving function with a two-cell, which is like an inequality, but here it's a two-cell, and some coherence condition which is required so that everything goes well. And this defines a category. So now we will want to define Cauchy completeness and skeletality on B categories, like it was for Q categories. And we will need another kind of morphism which adds to this structure, yielding we have the B categories, and we have two kind of morphisms, functors and distributors or profunctors. And yeah, this is a categorical structure. So a distributor will be a matrix where we had a B functor to be just a type-preserving function. A distributor is the matrix between two matrices. So in the case of quantaloids, what we had was that we had like the B categories could be seen as monads, and the distributors were just the morphisms between them in a category of matrices. Here we don't have the category of matrices, but we still have a concrete definition of distributors. So it's just a B matrix between the two underlying sets and a two-cell, which is a technical two-cell. But what happens is that there are some coherent conditions which are like B-module conditions. Because what happens is that actually distributors do behave a bit like B-modules, and we have like those kind of conditions. Those are not the exact conditions, but the conditions are like that, in a sense. So to compose distributors, we use a coend, meaning that this is a particular colimit, and this is why we ask to have local completeness and closed B category. And what happens is that the matrix M is an identity distributor for this operation, meaning that in particular M is idempotent, and we get a category of B category and distributor between them, which we can even make a bicategory by itself with some two cells defined coordinate-wise. So to express completeness, we will define the following notion of singleton. So singleton are really what a singleton will be something which is like a yoneda of element of the B category. So the particular singleton will be M-A, and recall that if we ask, for example, if we take the bicategory corresponding to the monoidal category of sets, monoidal Cartesian of sets, what we get is that M is just home because the B category will be the usual categories. So really, it's a Yoneda of A, and a singleton is a way to express what is something like Yoneda of A. So formally, it expresses as a distributor from some particular B category to MA, which has a right adjoint. So the right adjoint plays the role of MA dash. So we want to have something like an adjunction between a presheaf and a co-presheaf. And here, the ID star will be a very simple B category with only one element in the underlying set, which we'll call star, where star is an object of B, and the 1 times 1 matrix, which will just be the identity matrix. And so yes, what happened is that those M-A are singletons. And so we are brought to asking the following conditions. So a skeletal will be if M-A is equal to M-B, implies A equal B. So it's like asking that the Yoneda functor is faithful, and complete is asking that any singleton is of this form M-A. So any singleton is representable. So this yields a full subcategory of cat B, which we denote by cat kappa B, whose objects are skeletal and complete B categories. So for a quantaloid, what happened was that we defined the sheaves on Q as skeletal complete pair of Q categories, meaning that if we were to give a definition of sheaves on B, we will use this notion to define something like cat kappa of some bicategory obtained from B. And we have something which is interesting, that in the case of the B category associated to the Cartesian monoidal category of sets, we recover usual Cauchy complete B category because we ask that the adjunction between any data of presheaf and co-presheaf is representable. With some additional, yes? Yes, in this case, yes. In the case where you take the quantal of generalized numbers, extended numbers, you get Cauchy complete metric spaces. So yes. So in general, the category is not a topos because it contains the case of quantaloids, and also because it contains the case of quantaloids, and that quantaloids could be used to recover usual Grothendieck toposes. Any Grothendieck topos can be recovered as some cat kappa of B. So we are still investigating all properties of the category cat kappa of B, but we are going to present a plan to prove that we think that cat kappa of B can be expressed as a subcategory of the category of indexed categories over map B, where map B is the same bicategory of, it has the same objects as B, but the arrows are only those who have a right adjoint. So in a sense, they are the functional arrows. In the case of relation, having a right adjoint is a relation being functional. So we will create 3 functors between those 3 categories. So we have the category of skeletal complete B categories, the category of usual B categories, and the category of indexed categories of map B. And what we are going to do is to create those presheafs CP and int between those 3 to have this diagram. So we start by giving P, which takes a skeletal complete B category and yields an index category. So in essence, this is a bit of an inverse of the Grothendieck construction. And what will happen here is that the Cauchy completion condition will be crucial to define the action of maps on B categories. For example, if we have a B category MA, we want to get a function going from elements of A which are of type Y to elements of A which are of type X. So this is the action on the fibers. And what we will do is to say that if A is of type Y, f of A will be defined as the element which represent the singleton M-A composed with F. So this is a singleton if F is a map. And the Cauchy completion ensures that there is some element, and the fact that it is skeletal ensures that there is only one element. So what happens is that we get something which can be made into a functor going from skeletal complete categories to index categories over map B. In the other sense, we have a functor which is very much like the Grothendieck construction, which takes an index category and returns a B category. So really, it's like the Grothendieck construction. The local equalities is defined with a colimit. And what happens in general is that this construction does not yield necessarily a complete or skeletal B category. So we will need some completion functor taking some B category and yielding a skeletal complete B category. And this is the next functor, which is the Cauchy functor, which takes a B category and yields its completion, which is the B categories of singletons of it. So it happens that if we take all the singletons of MA, and there is some matrix which makes it into a skeletal complete B category. So here I denoted there are exclamation mark to denote left and right adjoint. So really it's just a matrix on distributors, on singletons. And what happens is that we get a skeletal complete B category. And again, this can be made into a functor taking a B category and yielding a skeletal complete B category, which sends MA to the set of to the B category of singletons of MA, and it also acts on the B functors by using the following fact, which is saying that there is a structure of equipment with pro arrows, which says that distributors are pro functors. Is that any B functor give rise to two distributors, to an adjoint pair of distributors. Here we wrote then F index exclamation mark and F power exclamation marks. And what happened is that using those distributors, which are just defined like that, we can define the action of this Cauchy functor on functors. So we have now this whole picture with those three categories linked with those functors. So what happened is that, first of all, the Cauchy functor is a left adjoint to the inclusion functor. So this was to be expected because it's a completion functor. This is what we wanted. And what we hope to prove is that cat kappa of B will be a left exact reflective subcategory of map B up to cat, so the index categories. So to this end, what we want to show is two things. First, we want to show that we have an adjunction C int with P, and that C int preserves finite limits. So we gave here what will be probably the unit of the adjunction, and the co-unit of the adjunction, we hope that it will be the identity, because we expect that the completion of already complete B category is still the same B category. As for perspectives, there have been several attempts to define enriched sheaves, notably by Borso and Quintero, as left exact reflection of C of V, where C is a V category and V is a monoidal category. So we want to see how this relates to those definitions of enrichment over B category, in particular in a case where V is the monoidal categories of abelian groups, which will deal like Grothendieck categories and linear Grothendieck toposes. And we have also a matricial formalism, like in Quantaloids, but this time what happens is that the join is replaced with a coend, which means that it's not necessarily idempotent. So what happens is that the coproduct, which generalizes the sum join, can be seen as a sum, while the composition can be seen as a product of matrices. So we really have a matricial formalism. So that's it, and here are the references for this presentation.